and welcome to lesson 4.6, mutually exclusive events. Last day we talked about the difference between independent and dependent events. However, today we're going to take a look at mutually exclusive events. Prior to doing that, we're going to do a quick warm-up here. 4.6. So the question says, what is the probability that you roll a 4 or a 5? So remember, or mathematically means we've got two cases, so we're eventually going to add. All right. So in order to do the probability of a 4 or a 5, let's look at their individual probabilities in the side margin. So the probability of rolling a 4 equals 1/6. And the probability of rolling a 5 equals 1/6. Okay? So in order to do the probability of getting a 4 or a 5, you just simply add the probabilities together. So it's going to be 1/6 plus 1/6. If you use your mathematics, that's 2/6, which will always be lowest terms 1/3. Okay, so there's a 1/3 chance or a 33.3% chance probability of rolling a 4 or a 5. All right. And folks, these are just independent events if you're curious about that. We're going to take a look now at our lesson for today. So mutually exclusive events. And here's what we're trying to learn today. We're going to identify when things are mutually exclusive or non-mutually exclusive, and we're going to calculate their probabilities. Okay, so let's take a look at this example. At the next assembly, there are 10 prizes that will be randomly selected to the winners. There's 5 t-shirts, 2 sweatshirts, and 3 gift cards. Okay. Now, Heather's the lucky person because Heather is the first winner and wants to win a sweatshirt or a gift card. Okay? So don't forget that when we take a look at that or, that we are going to, when we take a look at that or, that it's going to mean to add, right? Okay? So let's take a look at doing that. Okay? So instead of using a whole bunch of big words, we're going to let sweatshirt be SS for sweatshirt. And how about gift card? Let's use that GC. Okay? So how do we do this? Well, the probability of getting a gift card or a sweatshirt equals the individual probability. So what's the probability of getting a gift card? Plus, because it says or, the probability of getting a sweatshirt. Sorry, I'm in a little slant there. Okay. Well, the probability of getting a gift card is, how many gift cards are there? 3 out of a total 10. So it's going to be 3 10s. Okay. Plus, probability of getting a sweatshirt. There are 2 sweatshirts out of a total 10. Okay, put those together. And we should get 5 out of 10. Don't forget lowest terms. So that's going to equal 1/2. So therefore, Heather has a 50% chance of getting a sweatshirt or gift card. Okay, that's one way to do it, folks. Okay, I will show you the opposite because some people might like the indirect method. So that was the direct method. Here is your indirect method. Okay, so the opposite, if she doesn't want the opposite, so we know the probability of getting a the opposite is the t-shirt, right? Because she wants one of the other 2 others. So there's 5 t-shirts out of 10. Okay. So probability of not getting a t-shirt, which is prime, right? TS prime equals 1 subtract the probability of getting the t-shirt. Okay. Which is 1 subtract 5/10, which equals 5/10, which equals 50%, or 1/2 if you want to do it that way. Okay, so indirect, this is the same thing. So same thing, getting the t-shirt prime, which means the opposite, is the same as choosing to get the gift card or the sweatshirt. So either or method's going to get you the right answer, and you will both find that Heather has a 50% chance of getting her possible outcome. Okay, so another thing I'd like you to do, folks, is at the top of this, another way of talking about mutually exclusive events is what we call disjoint. Okay, so just write that up because that's another word that means mutually exclusive if the two events are disjointed. Okay, I'm going to talk about that down below, so just make sure you write that down. Okay. And the diagram, the Venn diagram, will probably help you here. Okay, so this idea only works if the events are mutually exclusive. Okay, that is, they cannot occur at the same time, which means, again, there's no overlap. Okay, also the event sets A and B are disjoint. Okay, all right. So just remember that because they're disjointed, there's no overlap. Okay? Okay? And what we want to remember is that the probability of getting A and B equals 0. Okay? And our formula for that, if you do A or 0, you can add them up individually, but notice because they're mutually exclusive, that means, so for example, you could either only be in set A or set B. You couldn't be in both set A and B. Okay? I could use the example that, you know, A is the percentage of it, the probability of it raining. Okay? Whereas B is the probability of not raining. Can it be raining and not raining at the same time? No. These are what are called mutually exclusive events. Okay? So they do not occur, which means the probability of both of them happening at the same time is 0. Okay? All right. Next is what happens if events are non-mutually exclusive. Okay? So if they're non-mutually exclusive, that means that they could both happen at the same time, right? So events can both or could both happen at the same time. Okay? And if they happen at the same time, folks, if I take a look at my sample space and I have a Venn diagram and I let one be event A, and to do event B, you could have an overlap, meaning they could occur at the same time. So if they're non-mutually exclusive, look for the overlap in Venn diagram, VD for Venn diagram. Okay? So you notice that there's a lovely little colored area there where they're overlapped. Okay? And if there's an overlap, what do we know? We know that the probability of A and B cannot equal 0. Because there's going to have to be a probability because it exists. Okay, so let's take a look at this, folks, in this next example. Okay, when drawing a card, what is the probability that when you draw one card, it is a face card or a red card? Okay. Okay, and remember, or means to add. Okay, so we're going to take a look at the probability of a red card first. Okay, well, there's two suits that are red. Each suit is 13, so it should be 26 over 52. Okay, simplify that to 1/2, because half the deck is red, half the deck is black. Okay, what's the probability of getting a face card? The probability of getting a face card is there a Jack, Queen, King, so there's 3 of them, times 4, which is 12, divided by 52. So 12 divided by 52 reduces to 3 over 13. What does that mean? Within each suit, there's 3 cards, the Jack, Queen, the King, that can be face. All right, so let's put these two events together. So probability of red or face, okay, equals the probability of red, okay, plus the probability of a face. But what do we have to remember to do, folks, is to notice that some of these face cards can also be what? Red. So you have to subtract the probability of red and face, right? So that's your inclusivity principle, where you add the two cases and then you subtract the overlap. Okay? All right. So probability of red from the sideboard there is 1/2, right here. Okay? Plus probability of the face is 3/13. Subtract, now we got to figure this out. How many red cards are face cards? Well, we've got the queen, king, and jack of diamonds, and we've got the queen, king, jack of hearts. So that's 6 total. So it's going to be 6/52. So don't forget that, because that's the overlap. Okay? So it's going to be together. If you want to put them all in lowest common denominators, or just use your fraction button, guys. So I'll just change it for those who may not have the fraction button in their calculator. So that goes back to 26/52 plus 12/52. Subtract 6/52. Okay. Plug it in your calculator, and it'll come to lowest terms of 8/13. Okay. If you're wondering where that comes from, you just multiply both of those by 4 to get your common denominator out of 52. But your lowest, always put it in lowest terms. Okay. And then remember, when we report on that amount, we change it to, usually we change it to a percentage. So therefore, approximately 61.5% chance of selecting a face or a red card. Just make sure your answer makes sense, folks, because we know the probability of checking a red card or selecting a red card is 50%. And so it should be more than 50% when you add on the probability of doing that or the probability of getting a face card. Okay, just make sure your answer is reasonable. Here, ladies and gentlemen, is your formula for non-mutually exclusive. It's actually the same principle. A or B is the union of it. And remember, you got to subtract the intersection of it. Okay? So here's a nice diagram for Venn diagrams. It shows the overlap, and that's the amount that you have to subtract. Okay? And just remember, we said it above, I'll put it in his box because it's important, that since they overlap, that the probability of A and B cannot be 0. All right? Okay, let's take a look at our last example before there's a video here. Okay, Jacqueline has 7 different colored shirts and 5 different colored pants. So 7 different colored shirts and 5 different colored pants. What is the probability she picks A, a blue shirt and a black pant, or B, a blue shirt or a black pants? Okay, so there's an and there's an or. So we're going to explain the 2 different situations. And means to do what with your options? You're going to need to multiply. Or means to add. And you're going to find that's a common theme throughout this course, ladies and gentlemen. All right, let's take a look at A. So probability of getting a blue shirt, BS, oh sorry, I'm going to say BS. This is a bunch of BS, folks, okay? And B, black pants, okay, equals the probability of your blue shirt times the probability of getting a black pants. Okay, so let's figure this out. Okay, so the probability of getting black is that she's got 1 out of how many different colored shirts? 7. Okay, so that's right up here. Because they're different, that means she's got all different colors. Okay, times, let's take a look at her pants. She has 5 different colored pants, so 1/5. Okay, plug that in, or use your calculator, or use your brain, and that's 1 out of 35. So therefore, there's a 2.9% prob of selecting blue shirt and black pants. Okay? All right, let's take a look at the next one. Okay? Blue, for B, blue shirt or black pants. So, or you've got to be careful here. Okay? Because it could be one or the other. Okay? So just make sure you know when we're taking a look at the probability of, again, BS and the union because, sorry, don't need that little tail on it. Okay? Just the union. Okay? And, or, that means or, so black, let's back up here. So we're looking for blue shirt or black pants, one or the other. Okay? So I want you to make sure you know that these are non-mutually exclusive. Okay, sorry, it's a spelling mistake. Okay. And just to make sure you know why they're non-mutually exclusive, because I could pick both of them, right? Because I could pick both of them. I could pick a blue shirt and black pants to make an outfit. So they both could occur at the same time. Okay, so let's take a look at that. So to do this probability, folks, remember we're using the formula from above for non-mutually exclusive. So it's going to be the probability of your BS. Sorry, I kind of get away with doing that. It's kind of fun. Hopefully you're laughing at me because you know me, I'm not much of a swear. Okay, and you add the probability of the black pants, but you got to subtract the probability where these guys meet. So BS and BP. Okay? All right. So let's figure that out. So the probability of getting a blue shirt is 1 out of 7. Okay? Plus the probability of getting black pants, because they're all different colors, it's 1 out of 5. Now, if you take a look here, folks, we have 7 different pants, and 7 different shirts and 5 different color pants. So 5 times 7 is 35 possible different options, and there's only one way that you could choose a black pant and a blue shirt. There's only one combination there, so it's 1 out of 35. Okay. Now we use our graphing. Just use your calculator. Plug them all together if you want. If you don't have a calculator with fraction button on, I'll put them all into denominators of 35 for you. So it's going to be 535 plus 735 minus 1 over 35. Okay? And, ladies and gentlemen, plugging that in, you've got 11 out of 35. Okay? That's lowest terms, but change it to a percentage. So therefore, there's a 31.4% chance of a blue shirt or black pants. Okay, and just remember, folks, that they overlap because you could have both of them as an option. Okay, so that's why they're non-mutually exclusive. All right, so one thing I want to make sure you write down here, folks, you're going to need this for some of your work, especially on your module and on your test. In order to test for mutually exclusive, okay, you check that the probability of A and B equals 0. Okay, means they can't happen at the same time, so the probability has to be 0. Okay, I also would like you to watch this video. I know some of these videos have an English accent and they say, well, give it a try coming up. So I find them funny. Maybe it's not this unit for sure, but some videos are pretty cool. Just give that one a check for mutually exclusive data sets or disjoint sets. You're going to see that word. Okay, and then folks, here's your homework. So page 340, number 1, 2, 5, 11, and try number 6. Have a great day, folks, and as always, come and see me for help. Au revoir.